In this video, I want to look at some of the basic properties of vector operations. In this case, I'm going to let u, v, and w be vectors in Rn. That tells me they have n entries, and all of those entries are real numbers. And we're going to let k and m be scalars. The first property, u plus v is equal to v plus u. We do have the commutative property of addition. The order of addition does not matter when I'm adding two vectors. Next, u plus v plus w is equal to u plus v plus w. So we also have the associative property for addition. When I'm adding three vectors, it does not matter which two I add together first. Next, u plus 0 is equal to 0 plus u, which is equal to u. So 0 is just a vector of all 0 entries, and if I add it, it works just like adding 0. It does not change anything. Next, u plus negative u is equal to 0, so adding the negative of a vector does get me back to that 0 vector. We then have our first distributive property. K times u plus v is equal to ku plus kv. I can distribute a scalar over vector addition. My second distributive property, k plus m times u is equal to ku plus mu. I can distribute a vector over scalar addition. Next, k times mu is equal to km times u. So if I'm multiplying by two scalars, I can multiply by the first and then multiply by the second, or I can multiply the scalars first and then multiply the vector. And finally, 1 times u is equal to u. Multiplying by 1 does not change a vector. So these are some of the basic properties, and there are some additional properties that we can easily deduce from these. The first, a scalar 0 times any vector results in the 0 vector. In order to show this, we know that 0 times the vector v is equal to 0 times that vector v plus the 0 vector. Next, we know that v plus negative v is equal to the 0 vector, so I'm going to replace 0 by v plus negative v. Next, I'm going to factor out a v from the first two. That gives me 0 plus 1 times v, and then plus negative v. We know that 0 plus 1 is 1. We also know that 1 times a vector is just that vector, so now I have v plus negative v. And from our basic list of properties, we have that that is equal to 0. So now I have 0 times any vector is equal to the 0 vector. My next basic property, any scalar times the 0 vector is equal to the 0 vector. In order to show that this is always true, let's let x be equal to the vector k0. And then I want to try to show that x is equal to the 0 vector. Well, we can say that x is equal to x plus the 0 vector, since adding the 0 vector doesn't change anything. I can then change the 0 vector to x plus negative x, since I know that is 0. I'm then going to change these two x's back to k0, since x is equal to k0. I can then factor out a k, so that I have k times 0 plus 0. We know that 0 plus 0 is 0, so now I have k times 0 plus negative x. K times 0 is by definition x, and now this is just x plus negative x, which we know is equal to 0. So now I have that x is equal to the 0 vector, which tells me that k times the 0 vector is equal to the 0 vector. So multiplying any scalar by the 0 vector will result in the 0 vector. Another result of these properties is that negative 1 times v is equal to negative v. So multiplying by negative 1 is the same as the actual negative of the vector. Let's do this by looking at negative 1 times v plus v. Well, we could factor out a v, then I'm left with negative 1 plus 1 times v. Negative 1 plus 1 is 0, so now I have 0 times v. And I previously showed that that was equal to the 0 vector. So now I have that negative 1 times v plus v is equal to the 0 vector. And we can subtract v from both sides to get negative 1 times v is equal to negative v. One last thing I wanted to define is a linear combination. So the idea of a linear combination is to have some vectors, multiply them by scalars, and then add them up. So let's suppose we have some vectors v1, v2, etc. up through vn, and we have some scalars k1, k2 up through kn. Then we're going to define this vector w, which is k1 times v1 plus k2 times v2 plus k3 times v3, etc., all the way up to kn plus vn. And that w is said to be a linear combination of the vectors. So let's look at some examples of this. Let's suppose I have three vectors that are given here. I could define a vector u as 2 times the first vector plus 3 times the second plus the third. And that would be a linear combination of these vectors v1, v2, v3. Another linear combination of these vectors, 7v1 minus 6v2 plus 8v3. The idea is just if you have a set of vectors, you can multiply them by scalars. In this case, we use 2, 3, and 1. Here we use 7, negative 6, 8. And then we add those results up. And this is a linear combination.